structure that they were putting in place. So cost parity is at the beginning of the decade, not at the end of the decade. Here's just another factor that's driving the business case in the industry towards battery electric vehicles. So now let's start to specifically talk about the opportunity for thermoplastics. And what we have seen is between the power electronics and the battery enclosure are the biggest opportunities for plastics in this new battery electric vehicle ecosystem. And specifically what we did is we went out and interviewed over 60 experts globally, ranging from OEMs, battery producers, major tier ones. And what we found was the industry is just starting to think about optimization of the battery design and optimization of materials. This is the opportunity for the thermoplastics industry, and this is the opportunity that I want to speak to you about here on the next page. And that's specifically what we've done is we've started to look at this battery enclosure space. What we've done is we've taken our EV Insider forecast to start to look at what that means. And what we see as we estimate the opportunity for thermoplastics around the battery enclosures will grow to be a $10 billion market opportunity by the end of the decade. And specifically, Dhanindra is now going to get into that into further detail. And again, before I wrap up, I just want to offer you, if you have any questions, please feel free to send me an email, and I'm happy to share additional research with you to answer your questions. Thank you very much. Dhanindra?
Thank you, Paul. This was very insightful. And in response to these industry trends and the optimization need, as Paul was explaining, I'm excited to share some of the bold new solutions SABIC team is working on to bring value to our customers. So traditionally, for batteries, steel and aluminum has been the incumbent materials. And here is an example of a large battery pack of a battery electric vehicle, which is 2.6 meter by 1.5 meter in size, so fairly large. We started looking at possibilities to reduce weight, improve performance, improve crash and safety, and achieve functional integration. So with these objectives, we re-engineered a solution with several of the structural components designed with plastic. So first one here is the top cover of the battery. It's an injection molded part in this engineered design made with our polypropylene long glass fiber resin under the Stamax family name with excellent FR properties. Same for the second component, battery modules, this yellow color parts which keeps the cells inside, battery cells inside with our both engineering thermoplastic resin family as well as a polypropylene short glass fiber resin family with excellent FR properties. The third component we have engineered in this battery pack is this orange color honeycomb part, which is a side crash protection member with our polyester chemistry with the Xenoy HDX resin. Since this battery pack sits on the floor, side crash is one of a very critical requirement, and the battery has to be protected, and the side members, if are engineered well to absorb the energy, then less load is transferred to the battery internal component and less chances of damage. The fourth component is a hybrid plate. So the bottom part of the battery pack we have engineered with combining metal and plastic together. These unique constructions not only bring structural performance and the shock resistance, but also bring thermal insulation and fire protection. Let me give some more details about these components in this page. We talked about the first component, pack enclosure, the blue color part here. It's a 2.5 meter by 1.6 meter large part, and you can see we have with the injection molding, there is a flexibility to encapsulate the battery control unit right inside the cover. So that has been engineered in the cover. The tray, which is the metal plastic hybrid construction, again a very unique design. We utilize the honeycomb geometry of the plastics and a thin metal cover in combination with plastic. This hybrid construction brings the good insulating layer for thermal efficiency. Also, metal in the bottom helps in spreading the fire in the case of fire test across the whole tray. And also, this unique construction brings the shock and impact resistance. The battery modules, this orange color part in the middle is another unique design where we have used the double wall construction for these module boxes for thermal insulations. We have a unique rip features on the lid so that the cells can be intact together inside this module box, as well as we have a provisions in the bottom of this module box to dissipate the heat. And the last component is the frame here, which takes part in a crash scenario. And we have this purple color honeycomb geometry made with our HTX resin in combination with the aluminum channel here to bring the side crash protection. We have years of experience in designing crash elements with plastics, industry first pedestrian energy absorber, industry first plastic bumper beam, and recently the industry first energy absorber for occupant protection inside the rocker we have brought to the industry, and we are leveraging our same experience in designing this crash element with plastic to protect the battery pack through designing these elements inside the side members. So with the unique resin solutions and combining it with engineering design, we have been able to reduce the weight by 30 to 50% for all the components that has been listed here, improve energy density, improve crash and safety of this solution, as well as achieve functional integration to reduce number of components. We'll share some more details of this design through a video. This is the battery pack I was talking about. It's a pouch cell battery as an example in this case, and the incumbent was an aluminum, and we engineered a plastic intensive battery pack for the components that I mentioned before. Now let's take a look on the video. Okay, so with this video, we shared some of the details of the designs, and to make this solution feasible, SABIC has been developing a brand new material portfolio to serve the industry needs for electrification. We have a brand new polypropylene resin family with short glass fiber and the long glass fiber resin compounds with excellent FR properties. And these resins are non-halogenated, non-brominated with a V0 FR rating at a very low thickness up to 1.5 millimeters. Then we have a polycarbonate-based resin compound, PCABS, in our Cycloy family, as well as polycarbonate compounds in our Lexan family. Plus, we have a polyester-based resin compounds for crash and safety applications. Along with the right materials, we have been developing unique design solutions to develop right applications. And some of these features you saw in the video, the side impact bar with honeycombs, the hybrid metal plastic tray, possibilities of integrating the cooling channels right onto the bottom tray that can bring significant amount of functional integration and reduce complexity of the battery tray. And also, through the process of plastic manufacturing, possibilities of several functional integration to bring ease of assembly. So with this unique material solutions and innovative designs, we have been able to reduce 10% weight at a battery pack level. Remember, we did not change the battery cells or the space frame in this particular design. Reduce number of components by 10% and increase the energy density by 15% through engineering and optimizing this battery pack with thermoplastics. Now I'll invite my colleague John Waters to share more about the performance of this engineered design and where we are with on the validation side. John.
Yeah, thank you so much, Dinendra. Appreciate that, and welcome everyone. It's a real honor and privilege to be speaking with you today. Again, my name is John Waters. I lead the technology innovation area at SABIC in advanced materials specifically applied to battery packs and electric vehicle structures. I'm fairly new to SABIC, joining the last year, but I'm not new to the battery pack solution set. I'm moving close to my third decade working on battery pack solutions in thermoplastics and in metals, of course. Reaching all the way back to the original program for General Motors, where I was the battery pack engineer for the EV1. And so it's a very exciting time, as Paul expressed and as Dinendra has expressed in the automotive industries. We see this huge ramp towards electrification and the commitment from not only the OEMs but all the tiers supporting that vision. And I thought to myself, if I was a tier one or an OEM, and I could put together a dream team of material scientists that were experts in electrification, it would look a lot like what SABIC has done and what we have done. And our global team, again, on all continents, we're in these verticals now, organized as a company and a corporation around materials, manufacturing, assembly, fire polymer interaction, and application verification. And Dinendra leads the market development for that. If you dive a little bit deeper into the material section, we're looking at things like fire retardancy, which is highly important, as you can imagine, short and long glass fibers for polypropylene and their engineering thermoplastics. In manufacturing, we're developing all the process solutions, the recipes, if you will, for thermoforming, injection molding, structural foam, compression molding, and profile extrusion, assembly, sealing and bonding, fire polymer reaction, FR transition, science testing, which is, I've got some good news to show you here in just a moment on some slides that we've got under test right now. Application verification, and obviously the battery tray, which in my opinion is kind of the foundation of the house. It's the structure that makes everything else work. So we're really dedicating a lot of time and energy and engineering to the tray in particular. Of course, the cover, the enclosures of the battery modules, and then all the other elements inside, in addition to electromagnetic interference, electromagnetic compliance solutions for the battery pack in itself. And then finally, the market development, as Dinendra so eloquently expressed here in the previous slides, literally looking at customer collaboration across all the engagement, across all these verticals. And so we've got a sort of a conveyor belt working with on all the circles there. So we're very united. We're meeting weekly, if not on a daily basis, as a cooperative team for customer applications. And so we're here at your service and excited about the future. And talking a little bit more about some of the functional testings we're performing, as many of you are familiar with, anesthetic requirements of large battery packs, which, these things are as large as a mattress, we like to say. We're looking at, of course, bending, stiffness, resonant frequency, torsional stiffness in these devices, evaluating against critical static requirements, OEM requirements, FMVSS, SAE, CE, United Nations shipping, drop testing, all comes in pack. Going to impact requirements. Obviously, there's the drop tests we're looking at, and we do all this with a very deep, very experienced CAE team that's doing FEA on our materials, which we know extremely well. Of course, they're all nonlinear materials, which takes a different set of skill sets and correlations over history, and we've got really decades of the correlation for making very accurate CAE designs, so that when you invest the money in the tooling and the part, that they're spot on for performance. So our plastic intensive battery pack has been evaluated against all of these impact requirements and all of our standard operating procedure for all of our designs coming down the pike as well. So just you guys are, most of you familiar, you guys and gals are familiar with the setup here of drop testing, physical tests. We've got those static and dynamic tests in-house, and we have strategic relationships with test facilities that we're performing these tests on, where we can get reliable impact prediction, again, going from the CAE to the physical test. With accurate performance there, you can kind of see how the closely aligned the graphs there are for reliable predictive engineering processes that allow us to really ensure success on, again, nonlinear advanced thermoplastics. And we won't go through all of this slide, but every OEM kind of has their own validation process, and we look at predictive validation from crash to stiffness to structure to FR to fire and others. We develop load cases with our customers. Obviously, we got target objectives we're trying to hit, and then we've got comparison with baseline and the intensive battery pack that Dinendra presented. We did all these with kind of agnostic or generic requirements that we hit according to FMVSS mostly, and we passed all those with flying colors with Thermoplastics. So we have no doubt that we can go head to head with metal solutions and provide extra value in thermal insulation, electrical isolation, part count reduction, improved crashworthiness, improved lightweighting. And all those add together with improved economics, right? So there are real challenges on the economics of the battery pack solutions in the market today and for the future. And in my opinion, the only way to get there is with thermoplastics and removing parts and improving obviously all the performance characteristics. So that comes to choosing materials, what's the right materials to choose, and again we've got a portfolio of advanced materials that are proven, that are in theater, if you will, in the marketplace, and have got millions and millions of miles of validation data on them, from short glass fiber polypropylene compounds to long glass fiber polypropylene compounds, which is a favorite of mine, the STAMEX. And ironically, the very first structural battery tray that was ever put on a mass-produced high-volume electric vehicle for the EV1 was a 30% glass polypropylene battery tray, and it exceeded all of our cost, mass, investment targets, our structural requirements for resonant frequency, our crash requirements, and of course the unitizing factor that it did in making the entire aluminum chassis at that time pass all of our stiffness, ride and handling, braking requirements there. All went through the structural battery tray. So very, very positive and bullish on this solution, and would love to explore not only that, but other solutions that we have for high temperature needs. For example, if your vehicle is going through an E-coat process, we can pass all those high temperature with our advanced materials as well. And I want to, speaking of temperature, I want to kind of move on to the fire retardancy here. We've got a short video, like a 20-second video to show you, but I want to, before we go to the video, I want to identify the part there on the left. That part is about the size of half of a door, maybe. It's a 4 millimeter thick Stamex material, 30% glass, long glass fiber on the floor. There's ribs there that are about 2 millimeters thick that are protruding up the walls and ribs. And we just subject the underneath of this to a flame, a Bunsen burner flame, about 1100 degrees Celsius. And we have got thermistors on there measuring the bottom temperature and the top temperature, going through. And so you'll see the last 20 seconds of this 5-minute test and how when we pull the flame away, that there's no fire. There's you'll see the intumescent reaction. We'll look at that in a moment. But if you go ahead and run the video, I think you'll find this pretty fascinating. Great. Am I back? All right. Super. Well, I hope you saw the performance there. We're pretty excited about that. And let me just show you a little bit more of the statistics. So before the test, you see the part on the left we showed before, and then you see the lower surface there, which you see the intumescent beginning to foam a little bit after the 5-minute duration. But I want you to notice there's no poke through. If you did that to an aluminum tray, you would have a hole right through your battery pack on that. And the upper surface there, you see just a little bit of degradation there of the heat coming through on top of the thermistor. But notice this chart here. You get temperature on the vertical axis, you've got time on the horizontal axis, and on the lower surface, the surface that was closest to the flame, or the bottom surface, you see the temperature being measured and going up to over 800 degrees Celsius. But notice on the other side of the wall, so to speak, you have the upper surface, or what's interior to the battery pack, or the battery modules, and we're below 200 degrees Celsius, and that's the skin surface. And so if you think about how we're keeping the flame, an external flame, out of the battery pack coming inside, or if a flame does develop on the inside of the battery pack, we're keeping it from going to the outside world. This is a huge advantage for passing the bonfire test on one and then thermal runaway on the other. So very excited about our FR capability, and we're actually changing the term. We're moving beyond FR to thermal shielding, to thermal barrier type capability with our thermoplastics. We're kind of wrapping up on different manufacturing technologies we're looking at. So we're looking at all the systems to make sure that we go from, again, SABIC, we just provide materials. That's our business model, right? The thermoplastic materials. But those materials have to go into application in success and survive through cost analysis, not only through part production and manufacturing process, but for the all-important warranty period for the complete 10-year, 150,000-mile durability for the battery tray that's required. So we are committed with the team that I showed you before to making all these processes work for our customers. So we're looking at low pressure injection molding processes. We're making large parts with that, compression molding with large parts, thermoforming for large parts to really go head to head with any kind of metal option that's really kind of dominant in the space today. So finally, just wrapping up, we've put together, again, a world-class team to serve our OEM and Tier 1 customers specifically in providing advanced materials that are reducing significant costs. I mean, we're talking up to 20 to 50% of cost reduction out of a full battery pack concept by utilizing part count reduction, improved crashworthiness, lightweighting, electrical isolation, thermal insulation and, of course, this FR protection that we've got going now. So I'll turn it back over to Dinendra, but we'll be happy to have discussions with you after this webinar. But thanks so much for your time.
Thank you, John. So here I will now summarize key takeaways. Plastic can bring significant value in optimizing this battery pack, and some of them are listed in this page. Can reduce significant weight from this battery pack, so 30 to 50% by components and about 10% at the pack level. Can improve the crash and safety from shock and the impact loads, reduce cost versus incumbent solutions, as well as plastic has inherent properties of thermal insulation, electrical insulations, and it does not corrode through galvanic corrosion. So these are the advantages that plastic can bring. Plus, processes like injection molding can enhance the functional integration opportunities and reduce number of components. And from SABIC side, we offer complete life cycle analysis support as well as the recyclable materials from our portfolio to meet the sustainability needs of our customers. And we can help. We bring unique material solutions. We are continuously developing next generation materials to serve industry need. And we bring the experience and expertise. It's a globally connected network of specialists within the SABIC who can help you, who can help meet your local needs and help you develop the optimized solutions using these wonderful material thermoplastics. With that, we are back to you, Lisa.
Oh, thank you, Dinendra, and John, and Paul. This has been a wonderful presentation. So much good information. Thank you so much. And now it's time to look at the questions from our webinar audience, and we certainly have gotten a lot of questions, so I thank the audience for that. On this slide is contact information for our three speakers. If you want to reach out to them directly for more content, or to stay informed about developments on electrification, or you want to follow them on the LinkedIn Showcase page. And now, our first question, and this is for Dinendra. Dinendra, what side crash loads and dynamic properties can the thermoplastic battery achieve? And are there physical test results? Dinendra?
Sure, Lisa. Very interesting question. And side crash is one of a very important crash phenomena. Happens at a vehicle level. FMVSS impact requirement or IIHS impact requirement here in America, similar in China and in the Europe. So in a pole hits the side of a vehicle and the loads are transferred to the battery. So and for this particular test scenario, we have engineered this plastic honeycomb solutions. During a crash, these plastic elements deform and absorb significant amount of energy and transfer with very little load back to the battery. And modeling a crash is a complex phenomena. So we have been developing several prototype parts of these honeycombs. We have done significant amount of physical testing here in Americas as well in Europe, and achieved excellent correlations through predictive correlations through validating material models. So yes, we have done the physical test at the component level, and then we have validated the performance at a full pack level through predictive calculations.
Thank you, Dinendra. John, you have the next question. Someone wants to know, what are some of the greatest challenges in the adoption of plastics for structural battery components?
I want to know who asked that question. No, that's a great question. It's the one I've been asking almost my entire career. So I've addressed that question from the OEM perspective with General Motors. I've addressed it from the Tier 1 perspective with Delphi. And now I'm addressing it really from a Tier 2 perspective with SABIC. And I think we're talking a little bit about a paradigm shift that's needed, right? When we go from the familiar world of metals, of steel and aluminum in the automotive industry to a thermoplastic, there's always a transition, especially when we start talking about structural components. So typically thermoplastics have been limited to interior trim parts that are not structurally load-bearing in significance, or more cosmetic or aesthetic in their application. But here we're talking about a battery tray, a battery cover, and battery module protection that have multiple use. And so if we can get into a systems engineering conversation with the engineer, with the product engineer, then that's a positive direction, right? So if we begin to look at it as a system where we're solving multiple problems at one time, or multiple challenges or multiple requirements with a single solution, that's the kind of conversation we need. But we have to break through the typical way vehicles have been designed and built and produced since Henry Ford, honestly, which is separate functional teams working on separate areas of the vehicle design. But the electrification vehicle, the EV, requires so much platform physics monitoring, right? Because it's really driven by mass and by friction of the tires and by aerodynamics of how much energy is required to move that vehicle from point A to point B. And when you're relying on a very expensive component like the battery, the lithium-ion battery, which is still very, very expensive in relationship to fossil fuels, we have to do more with less. We have to think more about the physical integration of systems to reduce costs from the manufacturing process to the warranty to the product design development and all the requirements around system efficiency and safety and reliability. So to answer your question succinctly, it's difficult to do, but I would just put a challenge out to the OEMs, the tiers in the room. Give us a chance. Let's enter into that systems conversation around battery pack and give us a chance on advanced thermoplastics to solve a lot of problems at once, including reducing system costs.
Thanks, John. Good to hear. Our next question is for Paul. How fast could plastics grow in EV battery applications, and will they grow more quickly for a specific electrified architecture? Paul?
Yeah, I would say from the research that we've done, we can see these applications for the battery structure to grow at more than a 20% compounded annual growth rate over the course of the next 10 years. And the major driver of that is the EV, the battery electric vehicle. Plug-in hybrids, mild hybrids, full hybrids, just are not going to have the size, the scale, the weight requirements that you see in the battery electric vehicle, and thus the battery electric vehicle is going to be the big driver. And that's why it's important to understand that as we look out at 2030, we see 1 out of 4 vehicles being a battery electric vehicle, and that's going to be the major driver of this portion of the market.
Thank you, Paul. John, you have the next question. Does this material pass China bonfire test?
Another great question. Our hypothesis is yes, but being an engineer, we're going to test it with data, and we're in process now of actually testing our large parts on the bonfire test as we speak. And if you want to reach out to me in 30 days, we'd be happy to show you those results.
Very good. Thank you, John. Let's see, Paul, this question is for you. What parts and systems that are done in plastics with an internal combustion engine will be most impacted by battery electrical vehicles? And what makes up the 30% content decline in plastics use in both battery electric vehicles and PH electrical vehicles?
Yeah, so let me just explain that real quick. So as we've embarked in this research with SABIC, what we've seen is the internal combustion engine components that go away that are really driving this 30% reduction are products like fuel tanks, it's engine covers, it's air intake manifolds, it's reservoirs. These are all the components that disappear with the battery electric vehicle. As we then started to look at, well, where is the growth going to come? I think it's important to know that the key areas are going to be specifically around the battery pack and the structure, which is the focus of the presentation here today, and then the power electronics. So the inverter, the DC-DC converter, the onboard charger. These are all the components that are great applications for plastic housings that will really drive this market to offset really the losses associated with the shift from the internal combustion engine.
Very good. Thank you. Thank you, Paul. Our next question is for Dhanendra. Dhanendra, what is the total weight of the solution?
Sure, Lisa. So we are looking for about 40 to 60 kilogram of plastic in this engineered design. Remember, it's a very large battery pack, 2.5 meter by 1.6 meter. And each of these components engineered with plastics bring about 30 to 50% weight saving versus incumbent steel and aluminum solutions.
Okay, very good. Thank you. This next question is for John. John, someone writes, it is easy to perform long fiber. They're asking, is it easy to perform long fiber FR material? And does FR degrade fibers in some cases? How do you manage this problem?
Yeah, we're evaluating that right now. I have personally developed thermal shielding intumescent material in long glass fiber Valex material previously, and we're actually applying that now to what you saw in the video was Stamex, which is the 30% glass, long glass fiber polypropylene. And so, speaking to my experts in intumescent attributes, they are actually optimistic on the longer glass fiber benefiting the FR performance. So we have encouragement in that with our formulation. Again, these are proprietary formulations that we have at SABIC that no one else has. Honestly, this is a great discovery that I've made since coming to SABIC. That anyway. So it's really phenomenal. So we're actually optimistic, enthusiastic about the contribution of the long glass fiber to the FR topic and performance.
Very good. Thank you. Thank you, John. John, we have another question here for you. Let me read it. An audience member writes, "This is a wonderful webinar. Thanks a lot." Well, thank you for that comment. I could attend with some... anyway, they're wondering if you already talked about electromagnetic barrier, so they wanted to know, is the electromagnetic barrier needed for the battery pack, and do you have a solution for electromagnetic protection?
John? Let's talk about that. Talk about EMI. This is a favorite topic of mine, especially in relation to battery packs. So. I've got a lot of experience around battery pack design engineering and dealing with this issue over the years. And I just want to clarify that the batteries produce no EMI, right? There's no electromagnetic interference coming out of electrochemistry. However, if that battery is connected to a switching device, such as an inverter or a motor, that cable is a conduit of EMI, right? So the cable itself, the power cable that comes out, and any other kind of box that's inside the battery pack that's doing switching and creating noise, if you will, is a culprit. And so it's very challenging to produce a Faraday cage around a battery pack as large as a bed mattress. Just so you know, there's a 1 millimeter diameter breach anywhere in the perimeter of that, then there is no compliance. There's no EMC. The electromagnetic interference is allowed to escape and you'll fail EMI testing. And so the real challenge is, how do we keep that sealed? So what I've done in the past is really try to focus on what's the producer of the EMI, what is that inside the battery pack, and address that at a local scale to get the interference down as small as possible so that it becomes benign in that. And we can do that with ferrite cores and different attributes of shielding the cables, et cetera. So that's where the focus should be. However, from the battery pack, we kind of have a belts and suspenders approach. And we are right now looking at, we can do inlays, we can do the Faraday cage inlays, but again, my experience says the flange is so large, and we'd have to put so many bolts in it's almost a very expensive solution. So we're looking at very inexpensive solutions in coatings that we're developing right now for our materials for the EMI purpose, and we'd be happy to dialogue with you further about your design, because we have a lot to bring in experience to the EMI conversation that's beyond the outside casing of that. So we would want to do a comprehensive solution set that's the lowest cost, most effective, and most durable over the warranty period of the vehicle.
Very good. Thank you, John. And this next question is for Dhanendra. Someone in our audience wants to know, are there any recycled grades, mechanical or chemical, available for the materials covered in this presentation? And are there recycled equivalents foreseen in the near future? Dhanendra?
Thanks, Lisa. Another very great question, as whole industry is looking for the sustainable solutions for next generation applications. From SABIC side, we have been keenly developing materials portfolio for recycled materials under our True Circle product family. So we have a mechanical recyclable materials, we have chemically recyclable materials, and also we are looking for the bio-based materials for sustainable solutions. So several of the resins you saw in today's presentations, we have the recycled versions under development, and these resins will be available to help our customers meet their sustainability needs.
Very good. And I want to thank all our speakers today for answering all these great questions from our audience and for their excellent presentations. And I also want to thank the audience for joining us. A survey will pop up on everyone's screen in a few moments. Please tell us what you thought of our program by answering just 3 questions. This webinar will be available on our website. An email will be sent to everyone who registered for it as soon as the archive is ready. Once again, thanks for watching.